Imagine a device that can heat your home in the winter and cool it in the summer, all while using less energy than you would expect. A machine that doesn't burn fuel or rely on glowing electric coils to create heat, but instead uses a physical principle that is more than 100 years old and is now becoming a cornerstone of the global transition to cleaner and more efficient energy. That device is the heat pump, a technology capable of extracting thermal energy from the surrounding environment, whether that's outdoor air, the ground beneath your feet, or a nearby body of water, and moving it to where it's needed, using the same science that powers your refrigerator and your air conditioner, even if you've never realized the connection. To understand how a heat pump works, you first need to recognize that heat is a form of energy that naturally flows from warmer areas to cooler areas, which means that to move it in the opposite direction, from cold outdoor air into a warmer interior, you need to do work to overcome the natural direction of heat flow. This is where the vapor compression cycle comes in, the heart of every heat pump and most cooling devices in the world. Inside a heat pump circulates a special fluid known as refrigerant, which has the unique property of evaporating at very low temperatures and condensing at higher temperatures, allowing it to transfer large amounts of heat during phase changes. In the first stage of the cycle, the refrigerant passes through a component called the evaporator, where it comes into contact with the outside environment, say, air just a few degrees above freezing. And thanks to its low boiling point, the refrigerant evaporates, absorbing heat from that air, even though to us it might feel like there is no heat to be taken. The now gaseous refrigerant flows into the compressor, an electrically driven component that dramatically increases the gas's pressure and, as a result, its temperature, a physical effect familiar to anyone who has felt a pump get warm while inflating a tire. This compression can raise the refrigerant's temperature high enough to heat water or air for your home's heating system. The hot, high-pressure gas then moves into the condenser, another heat exchanger, where it releases its stored heat to the indoor air or heating water, effectively warming your home. After giving up its heat, the refrigerant cools and returns to liquid form, passing through an expansion valve that drops its pressure and temperature, preparing it to enter the evaporator again and restart the cycle. This continuous process functions as a kind of thermal conveyor belt, moving heat from one place to another, and because of this, a heat pump can deliver several times more heat energy than the electrical energy it consumes to run the compressor. The efficiency of a heat pump is measured by its coefficient of performance, or COP, which expresses the ratio between the heat produced and the electricity consumed. For example, a heat pump with a COP of 4 produces 4 kilowatt-hours of heat for every 1 kilowatt-hour of electricity it uses, a level of efficiency no gas or electric resistance heater can achieve, because those devices cannonly convert energy from one form to another without multiplying the usable output. There are several types of heat pumps, categorized by where they draw heat from. Air-to-water systems that take heat from the outdoor air and transfer it to water for heating. Ground source systems that pull heat from the earth through deep boreholes or horizontal loops. And water source systems that extract energy from underground or surface water. Each has its own advantages and trade-offs, with ground source models generally offering higher and more stable efficiency in cold conditions, but requiring more complex and expensive installation. Although the science may sound complex, the principle is remarkably similar to what happens in your kitchen refrigerator. It works on exactly the same cycle, just in reverse. While the refrigerator removes heat from inside and dumps it into your kitchen air, the heat pump takes heat from outside and delivers it inside your home. Heat pumps are playing a critical role in the shift toward renewable energy, because the more clean electricity we supply to run them, the lower their carbon footprint becomes, making them both an economic and environmental solution for heating and cooling. When paired with solar panels or wind energy, a heat pump can become a highly sustainable system, replacing a significant portion of fossil fuel-based heating. That said, there are limits. The efficiency of an air source heat pump drops as outdoor temperatures fall, which is why in very cold climates they are often paired with backup heating systems, such as electric or gas furnaces. There is also the matter of higher upfront costs and the need for professional installation, because correct sizing and system design are critical for long-term performance. A heat pump is not just a piece of equipment, it is proof of how we can apply physical principles to solve real-world problems. in this case, providing comfortable living spaces with lower operating costs and a reduced environmental impact. And while the technology continues to evolve, its core principle remains elegantly simple: moving heat from where there is enough of it to where we need it most. Subscribe us for more videos.